Hubble's law. Edwin Hubble studied galaxies in a variety of ways. Not only did he look at the shapes of the galaxies and classify them, but he also started to measure distances to galaxies and how fast they were moving. And in addition to Edwin Hubble, he had an assistant, Milton Humason, who's an interesting character. He had no formal training in astronomy. Got involved because he was a mule driver who helped haul equipment and materials up when Mount Palomar Observatory was being built. And after it was built, he asked if he could come on as kind of like a handyman, and ultimately ended up working the telescope and assisting Edwin Hubble. And what the two of them found was an interesting relationship for galaxies. They found that the farther away a galaxy is, the faster that galaxy is moving away. So one, they found that all galaxies move away, which is an interesting phenomenon. And they found that how fast they were moving from us depended on the distance. And as you can see in the graph here, our vertical scale is the velocity of how fast it's moving away, and our horizontal scale is the distance, measured in megaparsecs, so that's millions of parsecs. And yes, there's scatter in this data, but overall there is a linear relationship between the two. And if you've got a nice straight line, that means you can make a nice, easy equation to represent this. And so that equation is what we now call Hubble's law. So V equals HR. V is our velocity, so that's how fast the galaxy is moving. R is our distance, measured in megaparsecs, so millions of parsecs. Hubble's constant, that's not one number there, and that's because of the scatter in the data. This is essentially the slope of that line of the graph. And because there's scatter in the data, we don't have a real fix on the value of Hubble's constant yet. This slide was made a while ago. The numbers now are actually a little bit better. It's probably somewhere between 74 and 76 for the value of Hubble's constant. And it was actually the Hubble Space Telescope, part of its goal was to narrow this number down, which it has. The units for Hubble's constant are awful looking. Kilometers per second per megaparsec, and that's really just so that the units work out, so that we've got kilometers per second for the velocity, megaparsecs for the distance. So let's look at how this equation is used. As an example, let's say a galaxy has a speed of 1,200 kilometers per second. Now, of course, that we're going to measure using the Doppler shift. And that we can do fairly easily. So, knowing a value for Hubble's constant means we can find the distance to the galaxy. So all those techniques that we looked at for finding distances to galaxies is really how we're figuring out the value of Hubble's constant. Once we really for sure know the value of Hubble's constant, then we can just use Hubble's law to find the distances to galaxies. So we're going to use Hubble's law, V equals HR. And in this case, our V is the 1,200, how fast the galaxy is moving. H, we're told, is 75 kilometers per second per megaparsec. So now we're just going to plug in. Put in the 1200 for the velocity, put the 75 in for Hubble's constant. So we get 1200 equals 75 times the distance, and that's what we're going to solve for. So to solve, we just divide both sides by 75. So 1200 divided by 75 gives us a value of 16 megaparsecs. Now, 1 parsec is about 3.24 light years. So a megaparsec is 3,240,000 light years. So multiply that by 16 if you wanted this number in light years. 3 times 16 is roughly 48 million light years. So we'll call it 50 million light years to round up. So the power of Hubble's law is it's an easy way to get distances to galaxies. So much easier than all of those standard bulb techniques. But the caveat is we need to know for sure the value of Hubble's constant. I've been using 75 for a long time, and it still works. And until they narrow it down to a precise number, I'm probably still going to use 75. But this is Hubble's law, and this is our way of easily getting distances to galaxies.